Now we'll discuss about rolling motion. When we talk about rolling motion, we can state for a round-shaped object, this rolling motion can be defined as combination of rotational motion and translational motion on a surface. So to be more precise, when we are given a round-shaped object on a surface, and if it is rotating as well as translating, the resulting motion we define as rolling motion. Like for an example, say if we are having a surface and we place a round-shaped object, say we place a sphere or a cylinder. It is moving translationally with some speed Vc and also rotating at an angular speed. About its center of mass we can denote as omega c, and this motion we define as a rolling motion. And this rolling motion can be considered as combination of translational motion of this body plus the rotational motion in the body about its center of mass. Like the rolling motion can be defined as a combination of rotation plus translation. Say there is a body, if it is rotating or say it is having rotational motion about its center of mass, then the body would be rotating at some angular speed. So every particle of body would be moving in a tangential direction to the motion about its center. And if we add the translational motion in the same, we can state in this situation, if the body is moving with a uniform speed Vc, then all particles of body will move with the same speed Vc. And if we combine the two motion, you can say each particle of body will have two different velocities. One is due to the translational motion and other is due to the rotational motion. Obviously, if it is rotating at an angular speed omega c, the particles on the circumference of the body will have a translational speed r omega c at every point on the circumference. So in this situation, we can state the center would be moving still with the speed Vc. The topmost point will have velocity. One is due to translatory motion, other is due to rotational motion. So it will be Vc plus r omega c. That will be the fastest particle in case of rolling motion, and the particle which is at the bottom or which is in contact with the surface will have one velocity Vc in forward direction and other velocity due to rotation is r omega c in backward direction. So for the bottommost particle, the speed can be written as Vc minus r omega c. If we talk about a particle at this position, so it will be having Vc in forward direction and r omega c is along tangential motion. So the two velocities can be added vectorially. This will give us the velocity vector of particle located at point P. So this will be the velocity vector. By vector sum we can calculate, and in the similar manner we can find out the velocity vector of different particles. Like if a particle is here, it will be having velocity due to translational motion in forward direction, and r omega c is in tangential direction. So by using vector addition we can find out its velocity as Vm if m is this position. So using vector sum we can calculate velocity vectors of various particles on the body which is in rolling motion. Now we'll discuss about different types of rolling motion in detail also. So we just talk about types of rolling. In general, at a fundamental level, we classify rolling motion in two ways. The very first we term as pure rolling, or this is also termed as rolling without sliding. and the other type we can simply call as rolling with a sliding. So let's analyze both the cases. One is pure rolling, which is also termed as rolling without a sliding, and the other one which is rolling with a sliding in detail. Now let's discuss the case of pure rolling in detail. Say we are having a round shaped object which might be a ring, disc, a sphere or a cylinder, which is translating at a speed vc and rotating about its center at an angular speed omega c. In this situation, if we just talk about the bottommost point, we can say that due to translational motion, it will be having a velocity in forward direction, and due to rotational motion, it will be having a translational tangential velocity r omega c in backward direction. So about this point, we can say if Vc is equal to r omega c, this implies the contact point will be at rest. The contact point will be at rest. So in this situation, if this contact point will be at rest, we can state Vc is equals to r omega c. And in this situation, the bottommost point will not slip on the surface on which the body is rolling. So we can state in this situation, if this point will be at rest, this also implies no dynamic friction, or which can also be considered as kinetic friction, will act on body. Because we know that kinetic friction acts only when there is a relative motion between the two surfaces. If this point will slide on the ground surface, then only kinetic friction will act. So in this situation, no kinetic or dynamic friction will act on body, and friction, if exists, will be static friction only. So here we can say if some friction exists due to the presence of external forces acting on the body, we can state that at the bottommost point of the body, which is the contact point, no kinetic friction will act, and if some friction is there, it will be static friction only. And for this we can also write if F external is present, the friction which will act at the bottommost point will be static, and if no F external is present, so we can state in situation when external forces are absent, the static friction will also be equal to 0, because the static friction will act only if there will be a tendency of motion between the two bodies which are in contact. So in absence of external forces, we can state no friction will act in terms of the roughness of the two surfaces, that of one of round shaped object and other that of ground. However, in this situation, a particular special type of friction will come in picture. We call rolling friction, about which we'll talk later. Right now, as we have studied about kinetic and static friction. So in this situation, when Vc is equal to r omega c, we can state kinetic friction will never be there and static friction will exist only if some external forces present on the body. Now we'll discuss about rolling with a sliding. This is the situation where we can say that the velocity of center of mass is not equal to r omega c for a rolling body. Here we are going to discuss about two cases. Let's first consider a case when Vc is more than r omega c for a rolling body. Say on a rough surface, if we place a round shaped object which is moving translationally at a speed vc and rotating about center at angular speed omega c. Here we can state the bottommost point will be having a translational speed vc in forward direction, and the speed due to rotational motion about center of mass is r omega c, which is in backward direction. So in this situation, if Vc is more than r omega c, that means the point of contact of the body with ground will move in forward direction as Vc is more. So if this will slide in forward direction, here friction will act in backward direction due to the roughness of ground, and the friction on ground will act, or the bottom surface will act in forward direction according to third law of Newton. In this situation, the friction will be acting in backward direction, and this friction is certainly kinetic friction as the point of contact is sliding. Now if we talk just about this kinetic friction, so this friction is acting opposite to the translational velocity of body. Then due to this kinetic friction, this translational speed is going to decrease. And if we talk about the torque due to this kinetic friction, that will be in clockwise manner, and that will have a tendency to increase this angular speed of body about the center of mass. So we can state, if in the beginning of motion, if Vc is more than r omega c, the friction is acting in backward direction in such a way that the higher component, which was Vc, will start decreasing, and the value which was lower omega c, it will increase. And certainly if translational speed is decreasing and angular speed is increasing, after some time we can state, after some time V final will be equals to R omega final. If V final is the final linear speed which will be less than Vc, and omega final is final angular speed which is more than omega c, after some time, when Vf becomes R omega f, then we can state pure rolling will start, and friction drops down to 0, which was initially Fk, which can also be written as mu n, if n is the normal contact force and mu is the coefficient of friction. In the similar manner, we can talk about its second case also, when Vc is less than r omega c. We consider the situation which is similar to the above. If there is a round shaped object which is having a translational speed Vc and angular speed omega c, but in such a way that Vc is less than r omega c, so for the bottommost point of contact, Vc is in forward direction and here r omega c in backward direction. But now as r omega c is more than Vc, this point will slide in backward direction. So here friction will act in forward direction, and on the surface, according to Newton's third law, the friction will act in backward direction. Now if we carefully analyze the direction of friction, it is in forward direction. So this will have a tendency to increase Vc, and the torque due to this friction is in anti-clockwise manner, that will oppose this angular speed. So this angular speed will decrease. So in this situation, again after some time we can state, here after some time again Vf becomes equals to r omega f, where Vf is the speed which is more than Vc, which was increased due to the friction, and omega f is the angular speed after some time, which is decreased due to the opposite torque acting on the body due to friction. So we can say when after some time this happens, again pure rolling will start, and as no external force is acting on body, again we can state friction is equals to 0. Similar situation you can analyze in both of these cases. And we can also state that whenever there is a situation, if no external force is acting and Vc is not equal to r omega c, that means the body is not in pure rolling, or the bottommost point of contact is sliding, then always friction will act in such a way so that after some time the body will start pure rolling and the friction will drop to 0. Let's discuss the situation of pure rolling of a body on inclined plane. Say at a height h above the level ground, a round shaped body is placed on the inclined plane, and say if it is a rough incline and it is released from rest, it will start pure rolling, and say when it will reach the bottom, it will attain a linear speed v and the angular speed omega. Then in this situation, we can easily find out the linear and angular speed at the bottom of incline by using energy conservation or the concept of work energy theorem. Here we can say for pure rolling, V is equals to R omega. Now, if we apply work energy theorem from the initial to the final point of body, then we can write using work energy theorem, we can write that initial kinetic energy of the body was 0, as totally the work done by gravity on it was mgh, and as we know in case of pure rolling, no work is done by the friction. So this equals to the final kinetic energy of body, and in case of rolling, the body will have two kinetic energies. One is due to translatory motion half mv square, and other is due to rotational motion which is half I omega square. And for a general body, its moment of inertia can be written as mk square, where k is the radius of gyration about the central axis of body. So it can be written as mk square into omega square. Here m gets cancelled out, and we can write omega as v by r. So the equation will be 2gh is equals to v square plus k square v square by r square. Here I have substituted omega as v by r. From this expression, I'll get the speed with which it will reach the bottom of incline as root of 2gh upon 1 plus k square by r square. This is the result which is quite useful, so keep it in mind. And in sequence, we'll also discuss that the same result can also be obtained by using the acceleration of body in pure rolling on inclined plane. Let's discuss that also. Let's find out the acceleration of a body in pure rolling on inclined plane. Let's consider a round-shaped body placed on a rough inclined plane at a height, say, h above the level ground. In this situation, it will experience its weight mg in downward direction, and the component of mg which is responsible for its motion would be mg sin theta, which is along the incline, and the other component of mg cos theta will provide the normal reaction acting on body. This angle would be theta. So due to mg sin theta, it will have a tendency to move forward. So it will experience a friction in backward direction which will provide a clockwise torque onto the body, due to which it will rotate with an angular acceleration alpha. And say it will move translationally with linear acceleration a, and we can write for pure rolling a is equals to r alpha. In this situation, if we just write down the equation of motion for this body, we can write for translatory motion, its equation would be mg sin theta minus friction is equals to ma. And for rotational motion, the only torque provided by the friction will be used. Here we can write it Fr is equals to I alpha. So angular acceleration we can write as A by R, as the body is in pure rolling. In this situation, this R we can cancel and take on the other side of equality. Now if we add the two equations, this friction gets cancelled out, and the expression we are getting is mg sin theta is equals to m plus I by r square into A. So this will give us the acceleration of body as mg sin theta upon m plus I by r square. And for a general body about central axis, we can write moment of inertia as mk square. If k is the radius of gyration of body, then this expression we can write as mg sin theta upon m plus mk square by r square. Here m gets cancelled out, and we can see the acceleration we are getting is g sin theta upon 1 plus k square by r square. This result you can keep as a standard result in your mind, and in many different type of cases this is going to be used. And if we are aware about the acceleration for a given object, if it travels the incline, at bottom it will reach with the speed v. The length of incline here we can write as this h by sine theta. So in this situation, the speed with which it will reach the bottom can be written as root 2 al. L is h by sine theta. On substituting these values, we can see the speed we are getting is root 2 gh upon 1 plus k square by r square. This is also a very useful result. In many cases, you need to apply. So be careful about both of these results.